This lesson is on linear inequalities. Let's begin by considering all the possible ways we could add two different numbers so that they would be greater than or equal to 3. We're going to consider all the pairs of x and y that satisfy this condition. To begin, let's just randomly choose a point like this one. What's this point? 3, 4. So what if x is 3 and y is 4? Does that satisfy the condition? Sure it does. 3 plus 4 is 7. That's greater than 3. What about another point? Do you think this one will? 4, 7? 4 plus 7? Oh yeah, that's way bigger than 3. So you can start imagining that any of these points over here on the right, top right, are definitely going to satisfy this equation. But let's start moving downwards towards where the boundary might be. Let's move in a bit. Does 2, 3 work? 2 plus 3? Sure. 2 plus 3 is 5. That's greater than 3. Let's keep going in. What about 1, 2? 1 plus 2? Hey, well that one is equal to 3. Does that still satisfy greater than or equal to? Yes, that does, but I don't think I can go any further. What if I had 0, 1? 0 plus 1 is no longer greater than or equal to 3. So this point cannot exist. Okay, well, let's keep moving around. What about this point? 2, 1. Can we go 2 plus 1? Hey, yeah, that's 3. Maybe we can keep going along this boundary line. Maybe there's a boundary line here. Let's try this. 0, 3, 0. 3 plus 0. Yep. What about 4 and 1? 4 minus 1? That's equal to 3. So you can imagine that any point here upwards should work. You can try any of these points. As we looked at before, if it's bigger than this boundary line of equaling to 3, then they should satisfy. So let's continue this pattern. It looks like the boundary is around here. Let's see if this point works. It looks like it's part of the pattern. 0, 3. Hey, nice. That's equal to 3. So you can imagine that x plus y equal to 3 is the boundary. Now, if you choose a point outside of the region that works, is it going to work? 0 plus 0, does that satisfy being greater than or equal to 3? No, it doesn't. So none of these points on this side of the boundary work. However, all of the points on this side seem to be satisfying our relationship. Pick some random points anywhere in this shaded area and see if they work. Now the boundary is seeming to look like this. Notice that the boundary, we have learned how to graph a line before. If you solve this, this was y equals negative x plus 3. Start at 3, go down 1 over 1, down 1 over 1. You've plotted all the possible points that work for the equation on the line, and now, because we have an inequality, we can choose a side to shade in all the other points that satisfy the inequality. So, graphing a linear inequality means that we should consider graphing the line equation. So just the line, whatever the line is. Choose a boundary type. So now notice that sometimes, say you had y equals negative x plus 3, and more specifically it said greater than or equal to. If it's equal to, then you're going to include all the points on the line. So if you have greater than or equal to, or less than or equal to, you're going to draw a solid line. Solid. That indicates that you're including all those points. If, for example, you had the same line equation, but you weren't including any points on the boundary, however, you were including everything all the way up to that boundary, greater than or less than, you would signify it as a dotted line. And that would imply that the points on the line don't exist, but all the points up to that line are fine. So it's like a border crossing. There's always that point at which you're in neither country, you're just in no man's land. Once you've chosen a boundary type and drawn your line, you can test a point to determine which side to shade. So you'll notice that as soon as one point works on that side, that whole entire side will work. You can check more points, but you'll notice they'll all be on the same side of the line. So if you choose a point and it works, shade that side. If you choose a point and it doesn't work, shade the other side. A really nice point to choose is 0, 0. 0, 0 is really easy to plug into an equation to check. Let's try this example. They want us to graph 3x minus 4y less than 12. So let's first graph the line equation. To graph the line equation, we could consider putting this into the form of y equals mx plus b so that we can figure out the slope and the y-intercept. So let's take 3x minus 4y equal to 12, and we're just going to consider the equal portion for now, and get y by itself. So subtract 3x from both sides, you get negative 4y equals negative 3x plus 12. Divide everything by negative 4, and you get 3/4 x minus 3. Notice the two negatives canceled. So we're going to start at negative 3 and go up 3 over 4. Up 3 over 4, up 3 over 4. What kind of boundary are we going to have? Well, in this case, the boundary is not included. So we need to have a dotted boundary. Now we want to check which side we need to shade. A nice point to test is 0, 0. Does 0, 0 work? Let's try it. 3 times 0 minus 4 times 0 less than 12? Well, that's just 0 less than 12. True. So since this point is true, that means it is included. That means every other point on this side of the border is going to satisfy the equation given. Next example, here we only have one variable, x. So you could take this as graphing one-dimensionally on a number line. You knew that, well, x is less than or equal to 2, so we're going to include the 2 and draw everything less than 2. However, they've given us a graph specifically so that we graph it on the two-dimensional plane. So when x equals 2, we know that y can be anything. So as soon as x is 2, everything else is going to work for any other y value. So if you remember, x equals 2 was the vertical line at x equal 2. Now it's including, so we want to include this border line, and we want to decide which side of this borderline we want to shade. Because it's less than, you can see that everything to the left is going to be satisfying less than 2 for the x values. You could test a point 0, 0, plug it in. Is 0 less than or equal to 2? Yes, it is. So therefore, this side works. Let's try this next equation. We first need to solve it a little bit so that we can get y by itself. So we have 3x plus 3y plus x equals 6. I'm going to look at just the equals bit so that I can draw the boundary. So we have 4x plus 3y is equal to 6. We want to get the x over to the other side, so 3y is equal to negative 4x plus 6. Divide everything by 3, you get y equals negative 4/3 x plus 2. So we're starting at positive 2, we're traveling down 4 over 3, down 4 over 3, or up 4, left 3, up 4, left 3. Now, what kind of boundary is this? Well, it's not including the boundary, so we need to draw a dotted line. Now we can choose which side of the dotted line to shade in. Let's choose 0, 0 because that's just such an easy point to calculate with. You can plug it into the original equation. If you had 0, 0, how would that work? Well, you'd have 3 times 0 plus 0 less than 6. Well, 3 times 0 plus 0 is 0. Is 0 less than 6? Yes, it is. So in this case, we can shade in that whole side. Notice that if it didn't work, then you would just shade the other side. Here's a bit of a word problem. Robert has up to $8,000 to invest in 2 different companies. If Robotronics stocks sell for $40 each and MacroCorp sell for $50 each, graph all the possibilities for his investment. So let's put Robotronic as X and MacroCorp as our Y. And we want to create an equation that relates these two. We know that every time he buys a Robotronic stock, he pays $40, so that's 40 times X. Every time he buys a MacroCorp stock, that'll cost him $50, which would give us $50 times Y. Now, he has up to $8,000, so together his whole entire investment has to be less than or equal to $8,000. So now we want to find a way to graph this. Therefore, let's solve it for y to get our line equation to get the border, the maximum amount that he can spend. All right, so let's move the 40x to the other side. We get 50y is, and I'm just going to do the equal sign here, negative 40x plus 8,000. And we want to divide everything by 50. And that gives us y equals negative, simplifies to 4/5 x plus $8,000 divided by 50 gives us 160. So if we look at moving by tens, we could draw this and keep this slope maybe as 40 over 50. We could count up 16. Let's see if we have that many. 2, 4, 2, 4, 2, 4, 2, 4. Just about. So this would be 160 up here, and we'd be going down 40, and each one of these is $10, and so on. So down 40, and over 50. Down 40, over 50, down 40 over 50, down 40 over 50. So basically, he could buy 160 stocks of Macrocorp and none of the Robotronics. Now, does that make sense? 160 times the $50 gives us 8 grand. So that would be all of his money spent right here. Over here, what's this number? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is 200 because we're skipping by tens. That's our scale. So notice he could spend 200 stocks of $40 each to give you the full 8 grand. Or he could mix and match at any of these other amounts. So this line here represents the potential possibilities of him spending all of his money on these two companies. But he could spend less. He could go and take 20 of these and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these. So he could take 20 and 12. He could take 10 and 10. He could take any smaller amount because this will result in spending less money, which he seems to be okay with. Notice I'm not shading anything in the negatives because in this case you can't take a negative number of stocks. Further, we could solve systems of linear equations. Remember, systems are when you're considering two equations at once. In this case, we're looking at two inequalities. So all we do is we graph them on the same grid and we look for the common region. The common region is the solution, and you just have to be careful about putting the correct boundary lines. So let's try this out. So take the first equation and let's resolve it so we can find our boundary line. Y equals negative 2x plus 1. So let's draw that. We start at 1 and travel down 2 over 1, down 2 over 1, down 2 over 1, up 2 left 1, and so on. What kind of boundary do we have for this first equation? Well, it's greater than or equal to, so it includes the line. Now let's check if this is going to satisfy the bottom half or the top half. So we want this to work. So let's check 0, 0. If this is 0, 0, plug in a 0, 0. 2 times 0 plus 0 greater than or equal to 1. Is 0 greater than or equal to 1? No, it's not. Therefore, this side is being shaded. All these points work. Let's take a look at the other equation in blue. So if we solve this, say you had x minus y is equal to 2. Let's solve it. That gives us y is equal to x minus 2. So that starts at negative 2 and travels up 1 over 1, up 1 over 1, and so on. Now this line is dotted, so let's just take a look at that. It's going to be a dotted line all the way through all these points. And let's check whether we shade in the top half or the bottom half. So always look at the original equation when putting in your point. So let's check 0, 0. Plug in zeros for your variables to check if this point works. Is 0 less than 2? Yes, it is. So we're going to shade in all of this top part here. So you can see that the overlap part is the part that is shaded with blue and with red. Let's accentuate that in green here. So all the way down to here, dotted line, and everything in this part is common. So if you use pencil crayons, it's actually might be a little nicer to visualize. Or if you shade it with a pencil, with the edge of your pencil, you'll notice that you can shade in darker the final solution. Let's take a look at another example. Let's graph the first component where x is less than or equal to 2. We've already done that one, and that one includes the line at 2. X equals 2 is a vertical line at 2, and everything less than that will be shaded. Let's do the next one in purple. We have y greater than or equal to 1. So y at 1 is right here, and it's also equal to. So we want to shade in everything that's greater than or equal to that line. So far we've got this part that's overlap. Now let's take this third one in blue. It's already solved for us, so we can start at the y-intercept of 2 and travel up 1 over 2, up 1 over 2, up 1 over 2. So all these points are on there, and it is not including the line, therefore we want to have a dotted line. Now we want to see which part do we shade. Do we shade the underneath or the over top? So plug in 0, 0 and check if 0, 0 works. Is 0 less than 2 plus 1/2 times 0? So is 0 less than 2? Yes, it is. So we're shading this whole bottom part. Now you want to accentuate the common region. Let's do that in green. We've got these points right here, and everything in between here seems to be filled in. So including these lines, all of these points, every single one, but a dotted line right there. In black, you can see that that shape there defines our solution for the 3 equations. Let's take a look at one last one here. The first equation is already solved for us, so we would start at 1 and go down 1, right 2, down 1, right 2, and it's including the line, so we want to draw a complete line. In purple, let's look at the next equation. We want to solve this, so 2y equal to negative x minus 2, y equal to negative 1/2 x minus 1. Starts at negative 1, goes down 1 over 2, down 1 over 2, down 1 over 2. And this one is not including. Now, how is the red supposed to be shaded? Well, let's check 0, 0 for the red. We've got 0 greater than or equal to 1 minus 1/2 times 0, which would be 0 greater than or equal to 1. True? False. Therefore, it's not including the 0, 0 point, so it's everything above. The other line, let's plug in a 0, 0 to that. We get 0 plus 2 times 0 less than negative 2. Is 0 less than negative 2? No, it's not. So that means we shade in not the 0, 0 point, but all the other points on the other side. So is there a solution to this? Are there any common points between these two inequalities? Certainly not, because these lines are parallel, they will never meet, and therefore will never overlap. And since they are shading in another component, it's impossible for there to be anything in common. So the answer to this would be no solution. So there is the possibility of having no solution for a system of linear inequalities.